Have you ever wondered if everything we think we know about our place in the universe might be completely wrong? What if the very ground beneath your feet, the solar system we call home, and every star you see twinkling in the night sky exists within something so vast and so empty that it challenges everything scientists have believed about the cosmos for decades? Tonight, we're diving into one of the most extraordinary discoveries in modern astronomy. A revelation so profound that it could rewrite our understanding of space, time, and the fundamental structure of reality itself. Scientists have found evidence that Earth and our entire galaxy might be trapped inside a colossal cosmic void, a bubble of near emptiness stretching 2 billion light-years across. And the most incredible part? The proof comes from echoes of the Big Bang itself. Ancient whispers from the birth of the universe that have been traveling through space for nearly 14 billion years. This isn't science fiction. This is cutting-edge research that emerged just months ago, presented at the Royal Astronomical Society's National Astronomy meeting. If these findings hold up, they could solve one of the most perplexing mysteries plaguing modern cosmology, while simultaneously forcing us to question whether our cosmic neighborhood is as ordinary as we've always assumed. But before we explore this mind-bending possibility, let me share something that might surprise you. The idea that we might live in an unusual part of the universe actually emerged from a crisis so severe that it's been keeping cosmologists awake at night for over a decade. They call it the Hubble tension, and it represents a fundamental breakdown in our understanding of how fast the universe is expanding. Picture this scenario. You have two incredibly precise measuring tools, both designed to calculate the same thing, the expansion rate of the universe itself. One tool looks at the cosmic microwave background, that faint afterglow of the Big Bang that bathes the entire cosmos in ancient radiation. This method gives us an expansion rate of about 67 km/s per megaparsec. The other tool uses nearby pulsating stars called Cepheid variables to measure cosmic distances. This method consistently returns a value of 73.2 km/s per megaparsec. Now, a difference of 6 units might not sound like much, but in the precise world of cosmology, it's absolutely massive. It's like having two perfectly calibrated rulers that give you completely different measurements for the same object. One of them has to be wrong, or there's something fundamentally broken about our understanding of the universe itself. For years, scientists hoped this discrepancy would disappear as measurements became more precise. Instead, the opposite happened. The more accurately they measured, the more pronounced the disagreement became. Multiple independent research teams using completely different methods kept finding the same troubling result. The universe appeared to be expanding at different rates depending on where you looked and how you measured it. This is where our story takes a fascinating turn. Sometimes the most revolutionary solutions come from the most unexpected places. Dr. Indranil Banik, an astronomer at the University of Portsmouth, had been thinking about this problem from a completely different angle. What if the issue wasn't with our measurements at all? What if the problem was with our assumptions about where we live? You see, modern cosmology has been built on a foundational principle called the cosmological principle. This principle assumes that on large scales, the universe is homogeneous and isotropic. In simpler terms, it assumes that matter is distributed roughly evenly throughout space, and that there are no special or preferred locations. Our cosmic neighborhood should be pretty typical, no different from any other region of space, billions of light years away. But what if that assumption is wrong? What if our galaxy, our local group of galaxies and everything within billions of light years of Earth, exists within a cosmic anomaly, a region so unusual that it skews every measurement we make about the broader universe? This is where the concept of the cosmic void enters our story. Imagine space as a vast ocean and galaxies as islands scattered across its surface. In most regions, these islands are distributed relatively evenly, but occasionally you might find enormous stretches of nearly empty water where islands are few and far between. In cosmology, these empty regions are called voids, and they represent some of the largest structures in the known universe. The particular void that Dr. Banik and his colleagues have been studying isn't just any ordinary empty region of space. They call it the KBC void, named after the astronomers Ryan Keenan Amy Barger, and Lennox Cowie, who first studied it extensively in 2013. This cosmic bubble of emptiness spans approximately 2 billion light-years in diameter, making it one of the largest coherent structures ever identified in the observable universe. To put that scale into perspective, light traveling at 300 million meters per second would take 2 billion years to cross from one side of this void to the other. Within this incomprehensibly vast region, the average density of matter is about 20% lower than what we observe in typical regions of the universe. It's not completely empty, mind you. It contains our Milky Way galaxy, our local group of neighboring galaxies, and the larger structure known as the Laniakea supercluster, but compared to the cosmic average, it's remarkably sparse. The truly remarkable thing is that our galaxy appears to be located very close to the center of this enormous void. Not on the edge, not in some random location within it, but right near the middle. This positioning is crucial because it means that nearly everything we can observe in the nearby universe is also within this underdense region. Now, you might be wondering how scientists could possibly detect something so vast and subtle. After all, empty space looks pretty much the same whether you're in a void or a typical region of the universe. The answer lies in those echoes from the Big Bang I mentioned earlier. These cosmic fossils are called baryon acoustic oscillations, BAO, and they represent some of the most ancient and fundamental signatures we can observe in the universe today. Imagine the universe when it was only a few 100,000 years old. At this time, space was filled with an incredibly hot, dense plasma composed of protons, electrons, and photons, all interacting intensely with each other. Within this primordial soup, tiny density fluctuations began to grow under the influence of gravity. Picture an overdense region within this cosmic plasma. Gravity tries to pull more matter toward this region, making it even denser, but the intense heat and radiation pressure push outward, resisting this gravitational collapse. These competing forces create something remarkable. Spherical pressure waves, essentially sound waves that propagate outward through the plasma at about 1/3 the speed of light. These cosmic sound waves traveled for approximately 400,000 years before something crucial happened. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This event, called recombination, suddenly made the universe transparent to light for the first time. The photons that had been trapped in the plasma were finally free to travel through space. But more importantly for our story, the sound waves that had been propagating through the plasma suddenly froze in place. These frozen sound waves became permanent features in the cosmic landscape. The regions where the waves had pushed matter together became slightly denser than average, while the regions they had evacuated became slightly less dense. Over billions of years, these tiny density variations served as the seeds for all the large-scale structures we see in the universe today. Galaxies preferentially formed in the denser regions, creating a subtle but detectable pattern in their distribution. The beautiful thing about baryon acoustic oscillations is that they provide a standard ruler for measuring cosmic distances. Dr. Bannock's team carefully analyzed more than 20 years of observational data on BBO and found something unexpected. The pattern of these cosmic sound waves in our local region of the universe appeared subtly distorted compared to what they should look like if we lived in a typical cosmic environment. The distortion was exactly what you'd expect if our measurements were being influenced by our position within a large cosmic void. Voids aren't just empty regions of space. They're dynamic structures that influence the motion of everything around them. Matter naturally flows away from under dense regions toward denser areas, creating large-scale velocity fields that can affect how we measure distances and expansion rates. Think of it like this. If you're standing in a river, the water around you is flowing downstream. If you try to measure how fast a leaf is moving relative to the riverbank, you need to account for the current. Similarly, if our galaxy is embedded within a cosmic void, all the nearby galaxies we use to measure the expansion rate of the universe are also influenced by the outflow of matter from this underdense region. This outflow creates additional apparent recession velocities on top of the normal cosmic expansion. When we measure the distance to nearby galaxies using their redshift, we're actually measuring this combined motion. The result is that local measurements of the Hubble constant appear artificially high, compared to measurements based on the cosmic microwave background, which reflects conditions in the early universe before these local peculiar motions developed. The statistical evidence for this void model is remarkably strong. Dr. Bannock's team found that their data supports the existence of a local void with odds of about 100 million to 1 compared to a void-free model. In the language of statistics, this represents overwhelming evidence that something unusual is happening in our cosmic neighborhood. But the implications extend far beyond just solving the Hubble tension. If confirmed, this discovery would fundamentally challenge one of the basic assumptions of modern cosmology, the cosmological principle. We would have to accept that Earth and everything we can observe exists within a cosmic anomaly, a region so unusual that it affects every measurement we make about the broader universe. This raises profound questions about how such enormous voids could form within the framework of our current understanding of cosmic evolution. The standard lambda-cold dark matter, RCDM model, which has successfully explained many features of the universe, struggles to account for structures as large and empty as the KBC void. Some researchers argue that voids this size simply shouldn't exist. According to our current theories of how cosmic structure forms and evolves, such a massive underdense region should be incredibly rare, if not impossible. The controversy extends to the very foundations of our understanding of gravity and dark matter. Alternative theories of gravity, such as modified Newtonian dynamics, MONAR, naturally predict enhanced structure formation on large scales, potentially explaining how such massive voids could develop. These theories also make different predictions about galaxy motions and cosmic expansion rates, offering testable alternatives to the dark matter paradigm that has dominated cosmology for decades. Recent observations have provided additional support for unusual large-scale motions in our cosmic region. Data from the Cosmic Flows for Galaxy Catalog reveals bulk flows of galaxies exceeding 400 kilometers over scales of 300 million light-years. These coherent streaming motions are larger than predicted by standard cosmological models, but align well with expectations for matter flowing out of a large cosmic void. The evidence continues to accumulate from multiple independent sources and observational techniques. Studies across the entire electromagnetic spectrum, from radio waves to X-rays, consistently suggest that we live in a region with below-average matter density, galaxy counts, measurements of cosmic background radiation, observations of distant supernovae, and studies of galaxy peculiar velocities all point toward the same remarkable conclusion. As we stand on the threshold of this potential paradigm shift in our understanding of the cosmos, we must grapple with the implications of living in such an unusual cosmic environment. The universe may be far stranger and more varied than we ever imagined, with vast regions of emptiness punctuated by dense cosmic metropolises. Our cosmic address may not be typical suburban space, but rather the equivalent of living in a cosmic wilderness, billions of light-years from the nearest major concentration of galaxies and dark matter. Yet, even as this extraordinary possibility takes shape before our eyes, the true mystery deepens when we consider what this cosmic void means for our understanding of time itself. You see, living within such an enormous underdense region doesn't just affect how we measure distances to nearby galaxies, it fundamentally alters our perception of cosmic history and the very age of the universe. When astronomers look out into space, they're simultaneously looking back in time. The light from distant galaxies has taken millions, billions, even nearly 14 billion years to reach our telescopes. This means we're seeing those galaxies not as they are today, but as they were when that light first began its journey toward Earth. It's like having a time machine that allows us to witness the universe's evolution from its earliest moments to the present day. But here's where the void hypothesis introduces a fascinating wrinkle in this cosmic time travel. If we're truly embedded within this enormous bubble of emptiness, then our observations of distant cosmic history are being filtered through billions of light-years of underdense space. The light from ancient galaxies, supernovae, and other cosmic phenomena has spent its entire journey traveling through a region where matter density is 20% below the cosmic average. This might seem like a subtle effect, but in the precise world of cosmology, even small systematic influences can have profound consequences. The gravitational effects of the void, the peculiar motions of galaxies within it, and the overall geometry of space-time in underdense regions all conspire to create systematic biases in our cosmic measurements. Dr. Bannock and his colleagues have been working to understand exactly how these effects might influence our estimates of fundamental cosmic parameters. The Hubble constant, which measures the current expansion rate of the universe, is just one piece of a larger puzzle. Other crucial measurements include the matter density of the universe, the strength of dark energy, and even the total age of the cosmos itself. Current estimates place the age of the universe at approximately 13.8 billion years, based on detailed analysis of the cosmic microwave background and our understanding of cosmic expansion history. But this calculation assumes that our measurements are representative of the universe as a whole. If we're actually observing from within a cosmic anomaly, these estimates might require significant revision. The implications become even more intriguing when we consider what this means for our search for life elsewhere in the universe. Cosmic voids aren't just empty regions of space. They're environments where galaxy formation, star formation, and the chemical evolution of matter all proceed differently than in typical cosmic regions. Within the sparse environment of a cosmic void, galaxies form more slowly and experience fewer gravitational interactions with their neighbors. The rate of star formation is generally lower, which means fewer heavy elements are produced and dispersed into the interstellar medium. The overall density of potentially habitable worlds might be significantly reduced compared to denser regions of the universe. Yet, there's another side to this cosmic coin. Voids are also quieter, more stable environments. Galaxies within voids are less likely to experience violent mergers or close encounters that could disrupt planetary systems. The lower density of matter also means less cosmic radiation and fewer catastrophic events that might threaten the development of complex life. Could it be that our location within this cosmic wilderness has actually been beneficial for the emergence and evolution of life on Earth? Are we living in a cosmic safe haven protected by billions of light-years of empty space from the more violent and chaotic processes that characterize denser regions of the universe? These questions take on new urgency when we consider recent developments in our understanding of cosmic structure formation. Advanced computer simulations of cosmic evolution have revealed that the universe's large-scale structure is even more complex and varied than previously imagined. Vast cosmic webs of dark matter filaments connect dense nodes, where galaxy clusters form, while enormous voids occupy the spaces between these cosmic highways. The KBC void appears to be one of the largest such structures ever identified, but it may not be unique. Other research groups have identified additional supervoids in different regions of the observable universe, suggesting that such enormous underdense regions might be more common than standard cosmological models predict. This raises profound questions about the fundamental assumptions underlying our current understanding of cosmic evolution. The LCDM model, which has been the standard framework for cosmology for over 2 decades, was developed based on observations that now appear to have been systematically biased by our unusual cosmic location. If the void hypothesis is correct, we may need to develop entirely new theoretical frameworks to understand how the universe actually works. The formation of such enormous underdense regions requires specific conditions in the early universe that aren't easily explained by current models. The physics of how matter flows out of these voids over cosmic timescales involves complex interactions between ordinary matter, and dark energy, interactions that we're only beginning to understand. Some researchers have suggested that the existence of supervoids like the KBC void might actually provide evidence for alternative theories of gravity. Modified Newtonian dynamics, or MOND, naturally predicts enhanced structure formation on large scales, potentially explaining how such massive voids could develop within the age of the universe. These alternative gravity theories also make different predictions about how matter should behave within and around cosmic voids. Unlike dark matter models, which predict specific patterns of galaxy velocities and clustering, modified gravity theories suggest that the apparent effects we attribute to dark matter might actually arise from our incomplete understanding of gravitational physics itself. The debate between dark matter and modified gravity theories has been simmering in the cosmological community for decades. The void hypothesis adds a new dimension to this fundamental question. If our local cosmic environment is genuinely unusual, it becomes much more difficult to test these competing theories using observations of nearby galaxies and cosmic structures. At the forefront of this unfolding mystery are the next-generation observatories poised to transform our understanding of cosmic structure and motion. The Rubin Observatory, with its legacy survey of space and time (LSST), will map billions of galaxies across half the sky, tracing the subtle distortions in their shapes caused by gravitational lensing. These distortions, like fingerprints left by invisible hands, reveal how matter, both visible and dark, is distributed across the universe. By precisely mapping galaxy clustering and the weak lensing shear patterns, LSST will allow cosmologists to test whether the apparent underdensity around us aligns with predictions from the LCDM model, or whether the geometry of space-time itself is subtly warped by phenomena beyond standard physics. At the same time, the Nancy Grace Roman Space Telescope will probe cosmic expansion with unprecedented precision, using distant Type 1a supernovae and baryon acoustic oscillations as cosmic yardsticks. Roman's deep infrared vision will penetrate far beyond the reach of current optical surveys, allowing it to chart the structure of the universe out to tens of billions of light-years, potentially revealing whether our local cosmic void is part of an even grander pattern of alternating overdense and underdense regions, extending across the cosmos. Meanwhile, the Euclid mission, already operational, is providing complementary data from its unique vantage point at the Sun-Earth L2 point. By measuring the shapes, redshifts and distributions of over 1 billion galaxies, Euclid is building a three-dimensional map of the cosmic web. Its findings could confirm whether the large-scale flows observed by Cosmic Flows 4 truly originate from our motion inside a supervoid, or whether other gravitational effects are at play. Gravitational wave observatories are also beginning to play a surprising role in this cosmic detective story. The upcoming Laser Interferometer Space Antenna, LISA, will detect ripples in space-time from merging black holes billions of light-years away. These gravitational waves carry with them a record of how the universe's expansion stretches their wavelengths as they travel toward us. By comparing the gravitational wave distances of these events with their retromander counterparts, a technique known as standard serene cosmology, scientists will obtain an independent measurement of the Hubble constant free from many of the biases that plague traditional methods. If LISA's results confirm a systematically higher local expansion rate, it would lend further support to the hypothesis that our region of the universe is indeed underdense. But beyond all the data, equations and simulations lies a deeper question, one that touches not only on physics, but on philosophy itself. What does it mean if we truly inhabit a cosmic void? What if our entire understanding of the universe has been shaped by an accident of cosmic geography? For centuries, science has worked under the Copernican principle, the idea that Earth and by extension humanity occupies no special place in the cosmos. It's a principle that stripped away the last remnants of geocentrism and gave rise to modern cosmology. But if the KBC void hypothesis holds true, that principle may no longer be absolute. It wouldn't place Earth at the literal center of the universe, but it would mean our vantage point is not typical. We may live in one of the largest and emptiest regions of the observable cosmos, a cosmic desert where galaxies are few and space expands faster than average. This realization challenges not only cosmology's assumptions, but also our own sense of cosmic belonging. Perhaps the universe is not uniform after all, not perfectly smooth on the largest scales, but textured, uneven, and full of vast, lonely expanses between the bright filaments of galaxies. And yet, within this emptiness, life has emerged, consciousness has awakened. Humanity on a small planet orbiting a modest star in a quiet spiral galaxy has begun to understand the structure of the very void that surrounds it. Maybe that's the true poetry of the cosmos, that in the most silent and desolate corners of existence, the universe found a way to see itself. The story of the KBC void is far from over. In the coming years, as new instruments come online and new data flows in, we may discover that the very space we thought was ordinary is in fact extraordinary, that the fabric of our cosmic neighborhood holds answers to questions about dark matter, dark energy, and even the fundamental nature of gravity. The void hypothesis doesn't just challenge our understanding of cosmic structure and expansion rates. It forces us to reconsider the very nature of cosmic time and the evolution of the universe itself. When we peer deep into space with our most powerful telescopes, we're essentially looking back through cosmic history. The most distant galaxies we can observe appear as they were when the universe was only a few 100 million years old, still in its cosmic infancy. These ancient galaxies are our primary window into understanding how cosmic structure formed and evolved over billions of years. But if we're embedded within a large underdense region, our view of cosmic history is necessarily filtered through this unusual environment. The light from those ancient galaxies has spent its entire journey traveling through space that may have very different properties from the cosmic average. This raises profound questions about how representative our observations of cosmic evolution actually are. The galaxies we see forming in the early universe, the rates of star formation we measure, and the chemical evolution of cosmic matter we infer from distant observations, all may be systematically biased by our location within a cosmic anomaly. The challenge becomes even more complex when we consider that cosmic voids themselves evolve over time. The KBC void we inhabit today may have had very different properties billions of years ago, when the light from distant galaxies first began its journey toward Earth. The underdense region may have been smaller, denser, or structured differently in the past. Understanding this temporal evolution of cosmic voids requires sophisticated computer simulations that can model the complex interplay between ordinary matter, and dark energy over cosmic timescales. These simulations suggest that voids do indeed grow and evolve significantly over billions of years, becoming larger and emptier as matter continues to flow toward denser regions. This evolutionary perspective adds yet another layer of complexity to interpreting our cosmic observations. Not only must we account for our current unusual location, but we must also consider how this location has changed over the cosmic time periods relevant to the observations we're trying to understand. The implications extend to some of the most fundamental questions in cosmology, including the nature of dark energy itself. Current observations suggest that dark energy makes up approximately 68% of the universe's total energy content and is responsible for driving the accelerated expansion of space. But these estimates are based on measurements that may be systematically affected by our location within a cosmic void. If the void hypothesis is correct, our local measurements of cosmic acceleration may not be representative of the universe as a whole. The apparent acceleration we observe could be partially due to the local effects of matter flowing out of our underdense region, rather than purely the result of dark energy acting uniformly throughout space. This possibility has led some researchers to propose that dark energy might not be a fundamental property of empty space, but rather an apparent effect that emerges from our unusual observational perspective. In this view, the universe as a whole might not be accelerating at all, and what we interpret as dark energy could actually be a consequence of large-scale inhomogeneities in the cosmic matter distribution. Such a radical reinterpretation of dark energy would have profound consequences for our understanding of fundamental physics. Dark energy has been one of the most mysterious components of the universe, requiring either exotic new forms of matter and energy or modifications to our understanding of gravity and space-time itself. If dark energy turns out to be an observational artifact rather than a fundamental aspect of cosmic evolution, it would eliminate one of the greatest mysteries in modern physics, while simultaneously creating new puzzles about the true nature of cosmic expansion and structure formation. The scientific community remains deeply divided on these radical possibilities. The observational evidence for cosmic acceleration extends beyond just local measurements, to include observations of distant supernovae in the cosmic microwave background. These diverse lines of evidence seem to confirm that cosmic expansion really is accelerating on a global scale. However, the void hypothesis adds important caveats to this interpretation. Even observations of distant supernovae could be systematically affected. If those supernovae are preferentially located in cosmic environments that are different from our own, the cosmic microwave background observations while less susceptible to local effects, still must be interpreted through theoretical models that assume homogeneous cosmic evolution. As we continue to unravel these cosmic mysteries, one thing becomes increasingly clear. The universe is far stranger, more complex and more varied than we ever imagined. What appeared to be a simple story of uniform cosmic expansion driven by dark energy may actually be a much more intricate tale of cosmic structure formation, local environmental effects, and observational selection biases that we're only beginning to understand. The void hypothesis represents just one thread in this increasingly complex tapestry of cosmic discovery. Whether it ultimately proves correct or not, it has already served a crucial function by forcing astronomers to question fundamental assumptions and explore alternative explanations for some of the most puzzling observations. As we stand at this crossroads in our understanding of the cosmos, the next decade promises to bring unprecedented revelations about our cosmic environment and our place within it. Advanced observational programs, sophisticated theoretical models, and innovative analysis techniques are all converging to provide new insights into these fundamental questions about the nature of space, time, and cosmic evolution. The echoes from the Big Bang that first alerted us to this cosmic mystery continue to reverberate through space, carrying with them the secrets of our cosmic origins and our ultimate cosmic destiny. In learning to listen more carefully to these ancient whispers, we may finally begin to understand not just where we are in the universe, but why we find ourselves in such an extraordinary cosmic environment. The story of the cosmic void is far from over. Indeed, it may be just beginning to reveal its most profound secrets about the nature of reality itself. The journey to understand our cosmic address has taken scientists down increasingly exotic pathways, leading to discoveries that challenge not just our understanding of space, but our comprehension of existence itself. As we dig deeper into the implications of inhabiting this vast cosmic wilderness, we encounter phenomena that stretch the boundaries of human imagination and force us to reconsider everything we thought we knew about reality. Consider for a moment what it means to live within a structure so enormous that light takes 2 billion years to traverse its breadth. The human mind struggles to comprehend such scales. If you could shrink the observable universe down to the size of Earth, the KBC void would still be roughly the size of North America. We're not talking about a small irregularity in cosmic structure, we're talking about a fundamental feature of reality itself. But here's where the story becomes even more extraordinary. Recent investigations have revealed that the effects of living within this cosmic bubble extend far beyond simple measurements of cosmic expansion. The void appears to influence the very fabric of space-time in ways that were previously unimaginable. When Einstein developed his theory of general relativity, he showed us that massive objects curve space-time, creating the phenomenon we experience as gravity. But what happens to space-time in regions where matter is unusually sparse? The mathematics suggest something remarkable. Underdense regions like cosmic voids don't just contain less matter, they actually create subtle but measurable distortions in the geometry of space and time itself. These geometric distortions propagate outward from the void like ripples on a cosmic pond, influencing everything from the paths that light rays follow to the rates at which atomic clocks tick. The implications are staggering. Every measurement we make, every observation we record, every fundamental constant we determine, could be subtly influenced by these space-time distortions created by our unusual cosmic environment. This realization has led some researchers to propose that what we interpret as the acceleration of cosmic expansion might not be driven by mysterious dark energy at all. Instead, it could be a geometric effect arising from the complex space-time curvature created by large-scale cosmic inhomogeneities. In this view, the universe isn't actually accelerating uniformly. Rather, different regions experience different expansion rates depending on their local matter density and geometric properties. The mathematical framework for understanding these effects draws on some of the most advanced concepts in theoretical physics. Researchers are developing sophisticated models that incorporate not just the distribution of matter and energy, but the dynamic evolution of space-time geometry itself. These models suggest that cosmic voids like the one we inhabit create complex gravitational fields that can mimic the effects of dark energy over vast distances. But the mystery deepens when we consider the temporal aspects of our cosmic situation. The void we inhabit today is not the same structure that existed billions of years ago when the universe was young. Cosmic voids grow and evolve over time, becoming larger and emptier, as matter continues to drain toward denser regions under the influence of gravity. This evolutionary process means that the cosmic environment we observe today may be fundamentally different from the one that existed when the most distant galaxies we can see were forming their first stars. The light from those ancient galaxies has been traveling through a cosmic void that has been continuously changing throughout their billion-year journey to reach our telescopes. Imagine trying to understand a movie by watching only the final scene, knowing that the theatre itself has been constantly renovating throughout the entire film. That's essentially the challenge facing astronomers as they attempt to interpret observations of the distant universe filtered through our evolving cosmic environment. The implications become even more profound when we consider quantum mechanical effects on cosmic scales. Modern physics suggests that empty space is never truly empty. Even in perfect vacuum, quantum fields fluctuate constantly, creating virtual particles that pop in and out of existence on timescales so brief they seem to violate the laws of energy conservation. But these quantum fluctuations don't occur uniformly throughout space. They're influenced by the local curvature of space-time and the distribution of matter and energy in their vicinity. Within a cosmic void, where space-time geometry differs from the cosmic average, quantum field behavior might be subtly altered in ways that could have measurable consequences for cosmic evolution. Some theoretical physicists have suggested that these quantum effects within cosmic voids could contribute to what we observe as dark energy. The reduced matter density in underdense regions might allow quantum fluctuations to behave differently, creating an apparent acceleration of cosmic expansion that emerges from the quantum properties of empty space itself. This quantum perspective on cosmic voids opens up entirely new avenues for understanding the relationship between microscopic physics and cosmic scale phenomena. The same quantum field theories that describe the behavior of subatomic particles might also hold the key to understanding why we observe accelerated cosmic expansion and why our local cosmic environment appears so unusual. The search for evidence of these exotic quantum effects has led researchers to examine the cosmic microwave background radiation with unprecedented precision. This ancient light, which has been traveling through space for nearly 14 billion years, carries subtle imprints of every cosmic structure it has encountered on its journey to Earth. Within the cosmic microwave background, scientists have identified patterns that might represent the signatures of quantum field fluctuations within cosmic voids. These patterns appear as tiny temperature variations that correlate with the large-scale structure of the universe in ways that suggest quantum mechanical origins. If confirmed, these quantum signatures would provide the first direct evidence that microscopic quantum processes can have measurable effects on cosmic scales. Such a discovery would revolutionize our understanding of the relationship between quantum mechanics and general relativity, potentially pointing the way toward a unified theory of quantum gravity. The implications extend beyond pure physics to touch on some of the deepest philosophical questions about the nature of reality itself. If our observations of the cosmos are fundamentally shaped by quantum processes occurring within our local cosmic environment, what does this tell us about the objectivity of scientific knowledge? This question becomes even more intriguing when we consider the possibility that cosmic voids might be more common than previously thought. Recent surveys of the distant universe have identified numerous other large-scale underdensities that rival or even exceed the KBC void in size and emptiness. If such structures are natural and inevitable consequences of cosmic evolution, then most observers in the universe might find themselves in similarly unusual environments. This statistical argument suggests that what we consider typical cosmic conditions might actually be quite rare. The dense, highly structured regions of the universe that contain most galaxies and stars might be cosmic metropolises where conditions are too chaotic and violent for the emergence of complex structures like planetary systems and biological life. From this perspective, cosmic voids represent not cosmic wastelands but cosmic sanctuaries where matter can organize itself into the delicate configurations necessary for complexity and consciousness to emerge. The very fact that we exist to observe the universe might be intimately connected to our residence within this vast underdense region. This anthropic interpretation of cosmic voids has profound implications for our search for extraterrestrial intelligence. Rather than focusing on the galaxy-rich regions of the universe, where most stars and planets reside, perhaps we should be looking for signals from other cosmic void dwellers, who, like ourselves, might have emerged from the quiet, stable environments that these underdense regions provide. The technological challenges of detecting such signals would be immense. Cosmic voids are, by definition, sparsely populated with matter and energy sources. Any civilization that emerged within such an environment would be separated from its nearest neighbors by distances so vast that even light-speed communication would take millions or billions of years. Yet these same vast distances might also provide advantages for advanced civilizations. The low background radiation levels within cosmic voids would make sensitive astronomical observations easier to conduct. The reduced gravitational interference from nearby massive objects would facilitate the construction of delicate scientific instruments and space-based observatories. Perhaps most intriguingly, the unusual space-time geometry within cosmic voids might offer unique opportunities for exotic physics experiments that would be impossible in denser cosmic environments. Advanced civilizations might find ways to exploit the geometric properties of underdense regions to achieve feats that seem impossible according to our current understanding of physics. These speculative possibilities highlight how much we still don't understand about the fundamental nature of cosmic voids and their role in cosmic evolution. As our observational capabilities continue to advance, we're beginning to probe these mysterious regions with unprecedented detail and precision. The James Webb Space Telescope has already begun to reveal surprising details about galaxy formation within cosmic voids. These observations suggest that star formation and galaxy evolution proceed very differently in underdense regions compared to typical cosmic environments. Galaxies within voids appear to form more slowly and retain more of their primordial gas content, creating stellar populations with unusual chemical compositions. These findings have important implications for our understanding of cosmic chemical evolution. The heavy elements necessary for planet formation and biological chemistry are produced within stellar cores and dispersed into space when massive stars explode as supernovae. If star formation rates are systematically different within cosmic voids, the abundance and distribution of these crucial elements might also be affected. Such chemical differences could have profound consequences for the emergence of life within void environments. Lower metallicity might reduce the probability of terrestrial planet formation, while also potentially creating more stable stellar environments, where habitable zones remain unchanged for billions of years. The interplay between these competing factors creates a complex landscape of possibilities for astrobiology within cosmic voids. While some conditions might be less favorable for life as we know it, other factors could create unique opportunities for alternative forms of biological organization that we haven't yet imagined. Recent advances in computational modeling are beginning to provide insights into these complex evolutionary processes. Sophisticated simulations can now track the formation and evolution of cosmic voids over billions of years, revealing how these structures influence everything from galaxy formation to the distribution of heavy elements throughout space. These simulations suggest that cosmic voids undergo dramatic transformations over cosmic time. Through the cosmic lens, we've journeyed deep into the silent expanses of the universe, into the vast and mysterious cosmic voids that stretch between the great filaments of galaxies. These regions, once thought to be nothing more than empty space, are revealing themselves to be dynamic laboratories, where quantum physics and cosmic evolution intertwine. What was once seen as absence may in fact hold the deepest clues about how reality itself is structured. The more we study these underdense realms, the more we realize they are not voids of nothingness but canvases painted by the faintest quantum fluctuations, ripples that may have shaped galaxies, stars, and even life. Every temperature variation in the cosmic microwave background, every whisper of expansion, carries the fingerprint of forces that connect the smallest particles to the largest cosmic structures. It's a reminder that the universe is a single, seamless fabric, woven together by invisible threads of quantum energy and space-time curvature. From a philosophical perspective, The discovery that we might live inside one of these immense voids reshapes our sense of cosmic identity. Perhaps our position in this vast emptiness is not accidental. Perhaps it's the quiet stability of our underdense region that allowed complexity and consciousness to emerge. The silence of the void might have been the cradle for awareness itself, allowing the universe to look back upon its own creation through the eyes of intelligent life. And if that's true, then cosmic voids are not just distant curiosities. They're essential to understanding why we exist at all. The calm between the chaos, the silence between the galaxies, these may be the spaces where creation takes its deepest breath. They might even be the cosmic sanctuaries where other civilizations scattered across the great darkness are watching us through their own lenses, wondering the same questions we ask today. This is the vision of Cosmic Lens, to explore not just the visible wonders of the universe, but the hidden truths that lie in its emptiness. Because sometimes to understand the universe, we must not only look at what shines, but also at what doesn't. Subscribe, stay curious, and keep your eyes open, for the cosmos still has secrets to share with those who dare to look deeper. Now, modern cosmologists must grapple with the possibility that our cosmic reference frame itself is highly atypical. The void hypothesis also raises intriguing questions about the anthropic principle and the apparent fine-tuning of physical constants that allow complex structures like galaxies, stars, and planets to form. If cosmic conditions vary significantly between different regions of the universe, perhaps the apparent fine-tuning we observe is simply a selection effect. We find ourselves in a region where conditions happen to be suitable for the emergence of observers like ourselves. Yet, even as we contemplate these profound implications, the scientific process continues to unfold with characteristic rigor and skepticism. Independent research groups around the world are working to verify, challenge, and extend the void hypothesis using different datasets and methodologies. Some studies have found evidence supporting the existence of large-scale underdensities in our cosmic neighborhood, while others have questioned whether such enormous voids are consistent with our current understanding of cosmic structure formation. The scientific community remains divided on the interpretation of the evidence, as is appropriate for such a potentially revolutionary discovery. The debate continues to evolve as new observations become available and theoretical models become more sophisticated. Computer simulations of cosmic structure formation are being refined to better understand how large voids form and evolve over cosmic time. Observational programs are being designed to test specific predictions of the void hypothesis against alternative explanations for the Hubble tension and other cosmological puzzles. What makes this scientific detective story even more compelling is the elegant way that seemingly unrelated cosmic mysteries begin to connect once we accept the possibility that we're living in this vast underdense region. The void hypothesis doesn't just address the Hubble tension, it potentially explains a constellation of puzzling observations that have been accumulating in the astronomical literature for decades. Consider, for instance, the peculiar behavior of our own galaxy's motion through space. The Milky Way is racing through the cosmic web at approximately 602 nanometers relative to the cosmic microwave background. This might sound fast, but it's actually surprisingly slow compared to what we observe for other galaxies in similar cosmic environments. Most galaxies show much higher peculiar velocities as they're pulled around by the gravitational influence of nearby massive structures. Our galaxy's relatively sedate motion through space has long puzzled astronomers. But if we're located near the center of an enormous cosmic void, this leisurely pace makes perfect sense. There simply isn't enough nearby matter to gravitationally accelerate our galaxy to the extreme velocities we see elsewhere in the universe. We're coasting through a cosmic desert, where the gravitational landscape is remarkably flat and gentle. This realization connects to another long-standing puzzle in cosmology known as the local group timing problem. Our galaxy and the nearby Andromeda galaxy are currently approaching each other and will likely collide in about 4 billion years. But when astronomers try to model the orbital dynamics of this local galaxy pair, they find that the timing doesn't quite work out according to standard cosmological models. The problem is that there doesn't appear to be enough matter in our immediate cosmic neighborhood to account for the gravitational binding of the local group. Either there's missing dark matter that we haven't detected, or the dynamics of galaxy interactions work differently than we think. But if we're embedded within a large underdense region, the reduced matter density naturally explains why local gravitational dynamics appear anomalous compared to theoretical predictions. The void hypothesis also sheds new light on observations of the cosmic web itself. When astronomers map the large-scale structure of the universe, they see a complex network of filaments and nodes, where galaxies cluster together, separated by vast empty regions. But our local cosmic neighborhood appears to be remarkably smooth and featureless compared to these distant cosmic metropolises. This smoothness extends to the cosmic microwave background radiation itself. When we look at the temperature fluctuations in this ancient light, we find that our local sky is unusually uniform. There are fewer hot and cold spots than we would expect based on the cosmic average. This phenomenon, known as the cosmic microwave background cold spot, has been another persistent puzzle in cosmology. If we're viewing the cosmic microwave background from within a large void, this apparent smoothness becomes much easier to understand. The reduced matter density along our line of sight to the last scattering surface would naturally create the appearance of a colder, more uniform region in the ancient cosmic glow. What appeared to be an anomaly in the cosmic microwave background might actually be a natural consequence of our unusual cosmic address. The implications ripple outward to affect our understanding of cosmic structure formation itself. The current theoretical framework suggests that the universe began in an almost perfectly smooth state, with tiny quantum fluctuations serving as the seeds for all subsequent structure formation. Over billions of years, these microscopic variations grew under the influence of gravity to become the galaxies, clusters, and superclusters we observe today. But this story of gradual structure formation has always struggled to explain the existence of extremely large-scale structures like the KBC void. According to standard models, it should be nearly impossible for such underdense regions to form within the age of the universe. The gravitational forces simply haven't had enough time to evacuate matter from such vast volumes of space. This is where alternative theories of cosmic evolution begin to look more attractive. Some cosmologists have proposed that the early universe experienced multiple phases of rapid expansion, not just the single inflationary epoch that's part of the standard model. These extended inflation scenarios could naturally produce larger-scale structures than conventional models predict. Other researchers have suggested that the dark energy driving the current acceleration of cosmic expansion might not be constant over time. If dark energy has evolved or fluctuated throughout cosmic history, it could have influenced structure formation in ways that standard models don't account for. Regions that experienced slightly different dark energy densities in the past might have evolved into the supervoids and superclusters we observe today. The most radical possibility is that our understanding of gravity itself needs revision on cosmic scales. Modified gravity theories, like MONDI, naturally predict enhanced structure formation compared to dark matter models. In these frameworks, the apparent effects we attribute to dark matter actually arise from our incomplete understanding of how gravity behaves when accelerations become extremely small. These theories make specific, testable predictions about how matter should behave within and around cosmic voids. Unlike dark matter models, which require the existence of exotic particles that have never been directly detected, modified gravity theories propose changes to the fundamental laws of physics that govern all matter and energy. The observational tests of these competing ideas are becoming increasingly sophisticated. Astronomers are now able to measure the three-dimensional positions and velocities of millions of galaxies, creating detailed maps of how matter flows through the cosmic web. These observations reveal complex patterns of streaming motions that extend across hundreds of millions of light-years. Recent analyses of galaxy velocity data have revealed bulk flows that exceed what standard cosmological models predict. Entire regions of the universe appear to be streaming in coherent directions at speeds of several hundred kilometers per second. These large-scale motions could be the signature of matter flowing out of enormous voids like the one we may inhabit. The velocity patterns also provide crucial tests of different theories of gravity and dark matter. Each theoretical framework makes distinct predictions about how galaxies should move in response to the underlying matter distribution. By comparing these predictions with increasingly precise observations, astronomers can begin to distinguish between competing explanations for cosmic structure formation. But perhaps the most profound implication of the void hypothesis concerns the fundamental question of cosmic representativeness. If our observations are systematically biased by our location within a cosmic anomaly, how can we ever hope to understand the universe as a whole? This challenge goes to the heart of the scientific method itself. Throughout the history of astronomy, we've repeatedly discovered that Earth occupies no special place in the cosmic order. We're not at the center of the solar system, our sun is not at the center of the galaxy, and our galaxy is not at the center of the universe. This principle of cosmic mediocrity has been a guiding assumption in cosmology for over a century, but the void hypothesis suggests that, while we may not be at the center of anything in particular, we may indeed occupy a highly unusual cosmic environment. This doesn't violate the principle of cosmic mediocrity in any absolute sense. After all, if supervoids like the KBC void are natural consequences of cosmic structure formation, then some observers must necessarily find themselves in such environments. The question becomes whether observers like ourselves are more likely to emerge in typical cosmic environments or in unusual ones. Dense regions of the universe experience more frequent galaxy mergers, higher rates of star formation, and more intense radiation environments, all of which could be harmful to the development of complex life. Conversely, the quiet, stable environment within a cosmic void might actually be more conducive to the emergence of intelligent observers. Planetary systems can evolve undisturbed by cosmic catastrophes for billions of years. The lower background radiation levels reduce the risk of mass extinctions caused by cosmic ray bombardment or gamma-ray bursts from distant stellar explosions. This anthropic perspective on cosmic voids opens up fascinating new avenues for thinking about the distribution of life in the universe. Rather than focusing our search for extraterrestrial intelligence on the dense cosmic cities where most stars and planets reside, perhaps we should be looking in the cosmic suburbs and wilderness areas where conditions might be more favorable for long-term biological evolution. The void hypothesis also has profound implications for our estimates of how common life might be in the universe overall. If most potentially habitable worlds exist in dense cosmic environments where catastrophic events are more frequent, the actual probability of complex life developing might be much lower than optimistic estimates suggest. On the other hand, if cosmic voids provide safe havens where life can develop and thrive over cosmic timescales, there might be entire populations of civilizations scattered throughout these underdense regions too far from the galactic mainstream to be easily detected by conventional search strategies. These speculations remain highly theoretical, but they illustrate how the void hypothesis forces us to reconsider fundamental assumptions about our place in the cosmic order. The universe may be far more varied and complex than we've imagined, with different regions offering vastly different environments for the development of stars, planets, and life itself. As observational technology continues to advance, we're gaining unprecedented ability to test these ideas against reality. The next generation of extremely large telescopes will be able to detect and study individual galaxies at distances that will allow us to map cosmic structure well beyond the boundaries of any local void. Space-based observatories, like the proposed Nancy Grace Roman Space Telescope, will survey billions of galaxies across cosmic history, providing the statistical power needed to definitively characterize our cosmic environment. These observations will reveal whether the patterns we see in our local cosmic neighborhood are truly anomalous or represent normal variations in cosmic structure. Perhaps most excitingly, advances in gravitational wave astronomy are opening entirely new windows into cosmic structure. As detectors become more sensitive, they'll be able to observe gravitational waves from increasingly distant and ancient cosmic events. These observations will provide completely independent probes of the matter distribution between us and the most distant reaches of the observable universe. The accumulating evidence from multiple observational approaches is painting an increasingly detailed picture of our cosmic environment. Each new measurement adds another piece to a puzzle that may fundamentally reshape our understanding of the universe and our place within it.